I'm Tony Lewis. I just joined BrainChip in November of last year. So a lot of the work I'm going to talk about is work that was where the foundation was really made by two of my co-authors here, Rudy and Olivier. They laid the foundation for this work a couple of years ago. This is in turn based on other work that's been going on for 40 or 50 years. But we finally figured out a way of putting it all together and doing some kind of interesting things. Oh, I just want to mention what's the spaceship doing, right? Okay. So earlier this year, we had a launch of one of our chips into space. There's a company called Ant61. They're looking at using neuromorphic chips to control robots in space, and so they just wanted to see how well neuromorphic chips do in near Earth orbit. If you're interested in learning more about that, I have a couple of podcasts. You can go to the BrainChip website. I interviewed a few people in this area. All right, so because this is the only thing about BrainChip that I'm going to get into, but a lot of you may not be familiar with us. We have an IP licensing model, so even though it says BrainChip, we don't really sell chips, so to speak. We've been around for a number of years, have lots of scientists working for us in all over the world, including Laguna Hills. So if you just drove up north for about an hour or so, you'd find us, and that's where both our corporate headquarters are and also our engineering. We have sites in Toulouse, France, and also in Australia. We are an Australian publicly traded company on the stock exchange, and we have a number of customers. Okay, so what's TENN and what can it do for you? TENN stands for Temporal Event-Based Neural Network. It's related to state space models, which are incredibly hot right now. So if folks are following the deep learning community, you've heard about Mamba, for example, and this is out of places like Stanford and CMU, and there's been some students who have formed corporations around this very recently and raised a lot of money. They can be used as a replacement for transformers for many tasks. Simon mentioned his great aversion to using massive amounts of energy to train transformer networks, and so we're trying to solve that problem. So you can use it for language models, for time series data, spatial temporal data, and we'll show you that it could dramatically lower energy requirements across all compute. Okay, so let's look at some inspiration. Everyone here is probably familiar with receptive fields in B1. There's an example of one on the right-hand side in green and red. And when I was getting my PhD in the 90s, one way of modeling these was to use a Gabor filter. It was pretty popular at the time. What's interesting about a Gabor filter is that it can be parameterized by a handful of symbols. And these symbols don't really understand anything about being placed on a grid, so to speak. And so they can be overlaid onto a grid of any resolution that you want. When deep learning came around, we started to build these little kernels that are on grids, and they lost some of the magic of Gabor filters. And there was quite a price that was paid. So on the right-hand side, we have an example of an arbitrary function, which presumably could be described by a handful of parameters. But then in the deep learning world, you have to sample at multiple points on some sort of grid. And if you change the grid, you have to do a resampling. Oh, by the way, if you learned on one grid, you can't transfer that to another grid. So that's problematic. And further, you get into this idea of when you look at temporal signals, you're going to have to discretize things in time. So, for people in neuromorphic engineering, that just should send chills up your spine. That sounds a lot like clock-based systems. We don't want to do that. But we're driven there by just the problem formulation. And, there's been overwhelming success. We can't deny that. But there might be other possibilities. Folks start to think about Legendre polynomials. as a way of representing some sort of kernel for temporal sequence processing. What's really cool about these Legendre polynomials, the math, we should really get into the math because it's marvelous and beautiful. And I'm a corporate executive and I'm saying this, it's like really worth delving into this. But what you'll find is that the polynomials can be represented as in a recursive format. And so this gives it some really magical properties. You can also look at Chebyshev polynomials, which the folks at BrainChip think is a better representation and has better properties. They also have a recurrence relationship. What can these orthogonal polynomials do for you? They can model any signal that you want, but with many fewer parameters than if you went with the conventional deep learning approach. You can convince yourself of this by just opening up Python, getting out NumPy, and there's plenty of fitting functions which will fit your Legendre polynomials to your favorite data set and do so with not a lot of parameters. Now, what can we do with this? Well, it turns out that because of this recurrence relationship in these polynomials, we can pass the problem of convolution as a recurrent neural network. And the beautiful part about this is that there's a duality. You can have two forms of exactly the same computation. You can have one form, which is a recurrence form, and you can have another one, which is more like a convolutional form. Now, if you've trained LSTMs and things like that, you may have encountered some problems. But what's nice is you can train things in the stable convolutional domain, and you can run them in this very fast, small footprint, recurrent domain. And over on the right-hand side, we have an example of a state space system, which, if you come from systems engineering, this is really familiar to you, where you have U as the input to a system. It goes through a matrix B or a vector B, and then it's projected into, it's added to AX. And A is some sort of thing that captures your system dynamics. And here, it's really something that incorporates properties of the polynomial. And then you can read this out through a C matrix and get your result. And then we pass everything through a nonlinearity. So if you come from a system engineering background, you're saying, okay, what is it now? What does it do? And then you stack all these things together. And so the output of one layer becomes the input of the next layer. And you're really scratching your head, like what does that do? Well, the weird thing is you can model a lot of very complex dynamics using it. And what it really looks like you're doing is you're doing a set of, say, generalized Fourier transformations, and then stacking them on top of each other. And in between these transformations, you have nonlinearities. You wouldn't think this would work, but it works for a wide variety of tasks. And most surprisingly, it works for language tasks. So what does language have to do with dynamical systems? Yeah, I wouldn't have predicted that. It's highly surprising. This is just a little picture which goes over how we can go from the recurrent domain to the convolutional domain just by doing a little bit of algebra. So I'm not going to get into this, but what you end up in the convolutional domain is this very nice structure that you have initialized using your polynomials, and then you fine tune it to achieve a little bit better basis. But you still get this property that you can have a very low dimensional fit. And so it works out very nicely. So Akita 2.0 has support. Gert asked me to talk a little bit about the architecture, so I'm just going to have a couple of slides on that. Basically, it's a digital event-based at-memory compute with on-chip learning. It's highly scalable. It's divided into a number of nodes, and inside each one of the node, you have 4 of these little neural engines, and one of those engines is dedicated to this sort of TENN's processing. We communicate through a mesh network, as I mentioned, and we're transmitting not spikes, but pieces of, but something a little bit more rich than spikes, so we contain additional information. See, that's this network, and then inside each TENN's processing unit or convolutional processing unit, we have some sort of event-based convolution. And so we have a comparison of classical convolution that you might see in a DLA. And for the example here, which is rather sparse, so this is the input, this is the convolution. You end up with doing a lot of work, even though there's a bunch of zeros coming in. And so this computation takes 225 max. On the bottom, however, you take, let's say this one goes through here, multiplies by this mask, and then it's more or less splat it onto the output field. I got the word splat from Toby Delbrick, and it's just very appropriate. And so it's like splats of paint. And so you splat one convolutional terminal, a kernel, the next one, but this is multiplied by a value, say 2, and the next one, and it all accumulates. And then you read that out and you pass it on to the next computational unit. So what's cool about this is that we benefit from sparsity, from activation sparsity. And it's like really a research topic of ours as to how to build networks that maximize sparsity. So I'm in charge of all the like the sort of the advanced research for the company, and I really like TENNs. And so this is just our research roadmap. It's not a product roadmap, so you're not all inside traders now, so you don't have to worry about that. This is the research stuff that we're doing, and we're looking at denoising. So we'll show some examples of that. And denoising is really hot for a number of fields. Keyword spotting. We're also thinking that we can adapt this to automatic speech recognition. In the generative AI space, we're looking at large language models. And by large, I mean small. So these are large language models, which are, say, under 1 billion parameters or so. We're looking at industrial IoT. So condition monitoring. You want to know if your machine is going to fail. Ideally, you take this very low power neuromorphic device, it's battery operated, you stick it on the side of your machine, and when it begins to groan and moan, you recognize that, and then you send a tweet to somebody. Oh, we don't say tweet. Has that been deprecated? We can't use. And then we have biomedical applications. So we're looking at EEG. We looked at EKG in the past. All sorts of things. So this is very the previous panel discussion on health applications was really very apropos. Now let's look at TENN's performance. So we look at a task which is sentence generation. So before I show you the demo, if you haven't seen a small LLM hallucinate, you're about to see that. So all that an LLM in its purest form, before you make it, you instruction fine tune it or anything like that, all it does is predict like the next word in a sentence. Okay. And so it may not be an exact copy of the training data. It may be something similar. And for the smaller models, it sounds a little bit like, it's a little bit wacky, and it improves with time. What I'm going to show here is that we do a comparison between our model, which is we call TENN here. We've trained on a thing called a Wikitext, which is about 1/10 of a gigabyte in size. And we're going to compare it against GPT-2, which is trained on 13 gigabytes of data, and GPT-2 small, 13 gigabytes of data, and also Mamba, which is the network I mentioned at the top of the talk, which is trained on the Pile, which is almost a terabyte of data. We have some scores here. These scores are negative entropy, as opposed to a perplexity score, because we think that the perplexity scores kind of exaggerate small improvements and in performance. So this negative entropy also has the advantage that the bigger it is, the better you're doing. And so we're landing here at a score of about 10.3, right in the middle. What's also remarkable is the number of parameters that we end up using. So in this third row, we showed that, well, we're using about half the parameters of GPT-2 small and, a fraction of the parameters of the large and full versions. But what's most important is the last line, which is the energy line. Okay, so parameters don't equal energy. They're separate concepts. So then, because in most deep neural networks, you reuse the same parameters over and over again for different computations. And so the energy use compared to GPT-2, well, GPT-2 takes 5,700 times as much energy. Okay, so 5,700 times. It's like that's a lot of trees. Like when you start training things, versus GPT-2 large, 13,000, and so on. Mamba is the nearest competitor, but still, we're using about half of the computations of Mamba. Okay, and now on the left-hand side, this is where the hallucination comes in. We have, if we can do things more efficiently, we should be able to generate output text faster. So on the left-hand side and the right-hand side, we have our model generating stuff, and we have a model, GPT-2, which is bogged down by unnecessary computation. And we have our log negative entropy score is better for ours than the one on the right-hand side. This is trained on trained on Wikitext, but it's prompted with the first 124 words of the Harry Potter novel. And it's all running on a single CPU, and so it's almost an apples to apples comparison. Our left side should eventually be much faster. Everything is in Python for this test, and there's just some issues with inefficiencies in Python, but we fully expect that we'll get several orders of magnitude faster in terms of our text generation. So faster also means lower power. We've also used TENNs for audio denoising, and we have a PEST score here. Our score is pretty competitive with state of the art. We use many fewer parameters, and we use about 1/10 of the max. And so I'm going to play you some samples. On the left-hand side are noisy samples of someone speaking. On the right-hand side, after we run this through our TENNs network. So let's see if we can do this.
When the sunlight strikes raindrops in the air, they act as a prism and form a rainbow.
Okay, so there's a little bit of noise back there.
When the sunlight strikes raindrops in the air, they act as a prism and form a rainbow.
Now we'll go to the noisiest one down here.
There is, according to legend, a boiling pot of gold at one end.
I don't know why they chose that quote, but...
There is, according to legend, a boiling pot of gold at one end.
Okay. So that's after denoising using our TENNs network, which is taking, roughly 1/10 the max and therefore power.
When the sunlight strikes raindrops in the air, the rainbow is a division of white light into many beautiful colors of gold at one end. The rainbow is a division of white light into many beautiful colors.
Okay, we'll stop all this. Okay, so this is the cocktail party problem. Just as an illustration, if I can move to the next slide without triggering anything.
There.
Okay, there. And then we can also use it for DVS style data. So this is an adaptation of the TENNs network. We have a couple of versions, and so the full TENN version achieves really good accuracy on the IBM DVS 128 data set. And so that's surprising. So we're doing things, the same concepts that we're using to do LLMs, we're using it to do spatial temporal event processing. So that's kind of cool. Okay, so what are the takeaways? What are the things I'd like you to walk away with? Well, TENN is highly power efficient. We can map it to our Akita 2.0 IP. It produces a state-of-the-art performance in areas, and we have a lot of exploration to do. Unlike Microsoft, the limitation on our budget is like how much I can put on my credit card. but in the future we'll have more money. And then we'd like to figure out how to enhance activation sparsity to take advantage of the Akita IP. And this polynomial space is really intriguing, and it would never have come into my knowledge set if I hadn't collaborated with the two physicists who are on my team. We have a number of openings like for internships. So over the summer, people are interested in spikes. People are interested in TENNs, just come and talk to me. And we also, love to talk and collaborate with folks. So with that, take questions.